All right, so here we are for part 2 of this. Sorry, my computer was acting weird. Part 2 of this section on graphing systems of linear equations, finding feasible regions. And so here we got a whole bunch of words, and we're supposed to somehow turn this into a system of inequalities, and then from there, make this into a graph of a feasible region. So let's go ahead and read through the problem and see what we got. A dietitian is planning a snack package of fruit and nuts, so it looks like if it's going to have fruit and nuts in it, those will probably be our variables, not sure yet. Each ounce of fruit will supply 1 unit of protein, 2 units of carbohydrates, and 1 of fat. An ounce of nuts will supply protein and carbs and fat. Every package must contain or must provide at least 7 units, at least 10 units, and no more than 9 units. Okay, so they give us our variables here. It says let x be ounces of fruit and y be ounces of nuts. And I'm supposed to turn this into a system of inequalities. Well, it looks like I've got information about protein, about carbs, and about fat. And I need to have at least 7 units of protein. So in the fruit, there's 1 unit of protein. So the protein from the fruit, 1 times the number of units, in this case ounces of fruit, plus the, let's see, the nuts is 1 unit of protein, so 1 unit of protein must be at least 7. Okay, so where are the ones from? The ones are from the, and let me get rid of some of this highlighting because it makes it sometimes harder to read for me. The 1 unit of protein and the 1 unit of protein, and it must be at least 7. At least 7 means 7 or more. Okay. What about the carbs? I got 2 units from the fruit, 1 unit from the nuts, and it must be at least 10. So 2 units from the fruit plus 1 unit from the nuts must be at least 10. And then the fat, I got 1 unit from the fruit, 1 unit from the nuts, and no more than 9. 1 unit from the fruit, 1 unit from the nuts, no more than 9. Okay. Now, this problem has something hidden in it, which we often refer to as the non-negative conditions. Hidden in the problem without being stated is the following: that x must be greater than or equal to 0 and y must be greater than or equal to 0. Because without saying it, it's implied that our variables can't be negative numbers because our variables represent the fruit and the nuts. Okay? So now that I've got my system, I can go ahead and graph this thing. Now the really, really nice thing about that non-negative condition down there is it lets me only use the first quadrant. Okay? So doing what I did before, I'm going to call this 1, 2, and 3. I know that my non-negative conditions say don't worry about over here, don't worry about down here, and don't worry about down here because we can't have negative variables. So the boundary line for equation 1 is going to be x plus y equals 7. So the x-intercept is 7, 0. The y-intercept is 0, 7. The boundary line for equation 2, or for inequality 2, is 2x plus y equals 10. It's going to have a inequality, let's see, I'm sorry, misspoke. It is going to have an x-intercept of 5 and a y-intercept of 10. Remember, I'm finding these intercepts by putting in the other variable as 0. So if y is 0, what's x? Or if x is 0, what's y? Okay. And then the boundary line for the third one is going to be x plus y equals 9, which has an x-intercept of 9, 0, and a y-intercept of 0, 9. Okay. So now I'm going to go ahead and sketch these things in. So the first boundary is going from 7 on the y to 7 on the x, and it goes through like this. Okay. I'm going to test the point 0, 0. 0 plus 0 is not greater than 7, so that means that we want this outside piece over here. Now I'm just going to go ahead and ignore anything outside of quadrant 1 to begin with. I'm just going to employ my non-negative conditions and just say it's this region right here. Okay. All right, I'm going to go ahead and graph that second one. That second boundary line goes from 5 on the x-axis, so that'd be about there-ish, to 10 on the y-axis, so that's up there-ish. So there we go. Okay. And then I'm going to test the origin. Is 0 plus 0 bigger than 10? Nope. So that means I want this side over here. And now I'll graph that last one. It's going from 9, remember that was 10 up there, so 9's just below it, to 9. So it's going to come in like this. And I'll test the origin. 0, 0 is 0 plus 0 less equal to 9, so that's a yes. So we want this side over, wait, I don't want to go that far. Whoa, I erased too much, sorry. I only want the part that's still in the first quadrant. So I just want what's under it. Okay. And now I'm supposed to figure out what part of this is pink and blue and yellow. It's all three. And I think that's going to be this in here, going up like that, down like that, and down there. And so it's going to have 1, 2, 3, 4 corners, and there's my feasible region. Now I know what you're thinking. Why are we graphing these things by hand? Couldn't we use the calculator, or couldn't we use Desmos or something to graph these? And you absolutely could. So let's go over here and bring up Desmos. Okay. And I'm going to start graphing these inequalities. So I'm going to have to flip back and forth here, so bear with me. My first inequality is x plus y is greater than or equal to 7. So x plus y is greater than or equal to 7. Okay. And then my second inequality was 2x plus y is greater than or equal to 10. 2x plus y was greater than or equal to 10. And then my third inequality was, let's see, that's the x plus y was less than or equal to 9. X plus y was less than or equal to 9. And then my fourth inequality was x must be greater than or equal to 0. And my last inequality was y must be greater than or equal to 0. And I will tell you now, looking at this thing, it's really, really hard to read this and understand what's going on. Because I'm looking for the piece of the graph that is shaded red and blue and green and purple and black. All right, so I'm going to show you a trick that is often used. What I'm going to do is I'm going to make the following argument. Rather than shading the part that works, I'm going to shade the part that doesn't work, the other side, and then when we get done, the part of the graph that isn't shaded will be the part that we care about. So since the red we want greater than or equal to, I'm going to have it shade less than or equal to. And since for the second one we want greater than or equal to, I'm going to have it shade less than or equal to. And the third one we wanted greater than or equal to, so I'm going to have it shade less than or equal to. The fourth one we want x is bigger than 0, so I'm going to have it shade less than or equal to 0. And then the fourth one we want greater than or equal to 0, so I'm going to have it shade less than or equal to 0. Did I get all that right? No, this one should be greater than or equal to 0. There we go. And now, when I look at my picture, the part that isn't shaded is my feasible region. And I can literally just touch on it and find all those corners really quickly. So I got a corner up top, a 1, 8, a 3, 4, a 7, 0, and a 9, 0. And there's my feasible region. Okay. So, of course, yes, if you really want to, you can graph these things by hand and try to see what's going on by hand. And it can be done. It's just really challenging to make an accurate enough graph to be able to get those values, get those points figured out. And then you have to do all those intersections to find all those corners, whereas Desmos does it for you. And so you could find your corners and we could say, okay, I've got corners 1, 2, 3, 4. This corner is 7, 0. That one's 9, 0. This one up here was, what, 1, 8. And that one right there was, I think it was 3, 4. I'd have to go back to be certain and check. Yeah, it was 3, 4. And there's my feasible region. Okay. All right, that brings us to the end of section 3.1. So I'm going to call it right there, and we'll come back and take a look at section 3.2 here, where we're actually going to give a definition to what we're going to be doing for the rest of the chapter. All right, see you back for part 2, or for section 3.2.